Hi, my name is Raphael. Welcome to my channel, where you learn more about computer graphics each week. Today, we will talk about anti-aliasing, a ubiquitous theme in computer graphics. Yet, before we can talk about it, we must know what an alias is. An alias is simply a reference to an object or nickname to a person. For instance, Raph is a nickname for Raphael. Aliasing in computer graphics happens when more than one function can be represented by the same pixels, which means they have the same reference. In general, a step-like function which resembles a stair. This occurs because every image in computer graphics is made of squares, or pixels, with an area greater than 0. However, lines and curves in geometry have length, but not thickness. This means that they need to be thick to be seen in a graphic display. Also, this means that a pixel is the smallest graphical object that we can plot in computer graphics. The only lines with no aliasing in the computer graphics are vertical and horizontal ones, parallel to a single image axis as they appear in a grid. All other curves have an alias. Anti-aliasing, or AA, tries to remove the stair effect by blurring edges. This process smooths curves and details. Of course, if done poorly, we'll lose essential image features and make our image look defocused. On the other hand, when done correctly, smoothing edges can increase the contrast of our lines and curves. Now, let's apply AA to the most straightforward line function, y equals x, or fx equals y. Without anti-aliasing, it's clearly a stair function. However, we will obtain AA if we add parallel lines on both sides with less saturated colors. We can do this by simply mixing the line color with its background, and we can do this for as long as we want. For instance, using x equals y plus 1 or x equals y minus 1 for 1 pixel unit, and then repeating this process for 2 pixels, 3 pixels, 4 pixels, and 5 pixels. In this manner, our main line has a thickness of 1 pixel unit, but a blur shadow of 10 pixels unit. The size of the blur is always our choice, but remember that it may reduce the image quality, as we have already shown. In my experience, 2 or 4 pixels of blur shadow should be good enough, which would make our line occupy 3 or 5 pixels at each unit step. By the way, Shaolin Wu's algorithm, which is a classic AA algorithm, uses only 2 pixels at a time. Back to our problem. There are 2 main types of anti-aliasing, or AA. Pre-rasterization methods are the ones that use geometry or 3D, 2D models, and post-rasterization ones that use the generated images. Some people prefer to talk processing instead of rasterization, just so you know. In this example, I have created a rotating line, and I have tried several algorithms using the pixels distance to the line on both of its sides and colored them accordingly. Shaolin Wu's algorithm does something similar, but uses the vertical difference between the line and a pixel, using pixels above and below the line to distribute color brightness. It is a pre-rasterization algorithm, but I've added a post-rasterization step, which is an oversimplification of fx AA The link for the full NVIDIA's white paper and Shaolin Wu's algorithm is at the description of this video. It takes some effort, but you can create a smooth line that fools our eye by combining post and pre-rasterization AA algorithms. Try it yourself. Test the line without AA and then try using one of the algorithms at the code or create one of your own. Oh, and maybe you have seen no difference between all the images you have already seen so far. That's probably because of the density of your monitor, which is a trick used by many Apple phones and computers. By using high-density monitors, we can avoid AA in some cases by creating pixels so small our eye can distinguish them from one another. For instance, my current monitor has 14 inches and has a resolution of 1920 by 1080 pixels. This gives me 157 pixels per inch, which is a median pixel density, according to the formula. Still, a high pixel density is at least 240 pixels per inch, according to Android's documentation. Apple's Retina monitor is usually a high pixel density screen. Still, most of our TV displays and our monitors are not. Now, we must talk about full-scale anti-aliasing, FSAA, another classic AA algorithm. It divides pixels into subpixels using the original geometry for obtaining a better color sample. Once a pixel is divided, we can mix the colors of the subpixels using any filter that we want. Still, for this video, we will always use the mean filter, which averages nearby colors. FSAA main idea is to create a virtual image greater than our final image to downsample it to our desired image size. In this example, I have implemented SSAA or FSAA times 16 using evenly spaced subpixels. Since pixels naturally create an integer grid, we can fill the space between integers with several subpixels. Using 16 means we have divided the x and y coordinates intervals by 16. This generates 256 subpixels of size 0.0625 pixel units or 6.25 centipixels. The sun is a yellow circle in this image, and we define its center dependent of time. For each pixel, we determine that if its distance to the center is smaller than its radius, it should be painted yellow. We count the number of subpixels that are inside the sun, border or not, and linearly interpolate between the sun color, SG color, and the background color, BG color. The resulting color becomes our new background, since we will now interpolate between it and the mountains in the next step. I have used a JSAA jittery sampling anti-aliasing for the mountains. This technique is similar to FSAA. Still, I have used only 16 subpixels by adding some randomness to our evenly spaced samples. I will explain the power of randomness in another video. The stars are the first thing that we create and are added to the background. They don't need AA, since they are a naturally smooth function. The faster algorithms for AA detect where borders and contrast transitions occur to apply a filter only at those regions, since not every part of an image needs AA. We have seen, for instance, that the star models didn't require AA, and in general, low color variance regions don't need it. At last, I present you as an example the cousin of the Apple's beach ball. I've used a blend of trigonometry, shadows, color mixing, and the smooth step function. an excellent function of GLSL that we will explore later to motivate some of you. As an exercise, I propose that you create the yin and yang symbol, which add two small circles to this last example, and smooth them using AA. Even if you don't understand what this previous code does, it is good practice to try adding features to other CG codes. That concludes our lesson. I hope that you have learned something today. Feel free to ask questions in the comments or send me an email. I'll get back to you as soon as I can. Next week, we will meet again to learn more about computer graphics. See you then.